Hey everyone, welcome back and let's write some more Leetcode today. So today let's solve minimum cost to connect all points. And surprise, this actually is not a problem from the blind 75 list that we've been working on recently. And the reason I'm solving this problem is because honestly, it actually should be a part of that list. Like this is one of those problems I think that's missing from the blind 75 list. Reason being is this is a problem related to minimum spanning trees, a concept that a lot of people skip over, I think, when they grind Leetcode. So this is what we're going to be doing today, and you might have heard of an algorithm for minimum spanning trees. There's actually a couple, Prim's algorithm, and there's also Kruskal's. We're going to be doing Prim's algorithm because I think it's easier to implement and it's actually more efficient most of the time. And you might remember this algorithm from college. Most computer science curriculums do teach it, but if you're anything like me, you probably forgot it the instant that you finished the class that you learned it in. But that's okay. And this algorithm, Prim's algorithm, is actually not as complicated as you might expect. So we're just given a list of points that represent some coordinates on a 2D plane. So for each point, we're given two values, the x coordinate and the y coordinate. So the cost of connecting any two particular points, like let's say these 2 points circled down there, the cost of connecting them is just going to be the absolute value of the x difference plus the absolute value of the y difference. So it's actually not, the cost of connecting them is not going to be like the diagonal. It's going to be the x distance and the y distance. In other words, the Manhattan distance, if you've heard of that term. That's pretty easy to calculate, good for us. And for the entire set of points, in this case, we're given 5 points. We want to know what's the minimum possible cost to connect all points. And they also say that any pair of points is going to be connected by exactly one simple path. I think that information is actually redundant. Just saying that we want the minimum cost to connect all points pretty much tells you this is going to be a minimum spanning tree problem. So the only question is, where the heck are the edges for this graph? We're only given points, right? But they do tell us pretty much what an edge is going to be, right? With the cost of each connection is just going to be the distance. So we have to create our edges ourselves. So basically, all possible edges could be, every single point to connect it to every other point, right? That's going to be a set of edges, and we can continue that. So for example, this point to connect all the other points as well. So we're going to have to kind of manually create the points. So for each pair of points in the entire graph, we're just going to take the Manhattan distance between them and just call that an edge, and then, have our list of edges, or basically we're going to create an adjacency list. So that is kind of like the pre-work we have to do. That's step 1 in this problem, creating the edges. But as soon as you create the edges, this is literally just a problem that you can go ahead and take Prim's algorithm and just apply the textbook definition of Prim's algorithm to this problem, and you will get the optimal solution. And the time complexity of that is going to be n squared log n, because n squared is going to be the number of edges we're going to have, right? Because to connect each pair of points, we could potentially have n squared edges, where n is the number of points that we're given, and log n is going to come from Prim's algorithm because we're going to be using a min heap in this problem. So it's pretty similar in a way to Dijkstra's algorithm, Dijkstra's minimum path algorithm. If you are familiar with that, Prim's algorithm is pretty similar to that. So let's jump into it. So Prim's algorithm is an algorithm to find minimum spanning trees. So there's a few concepts you have to be familiar with to understand Prim's algorithm. Obviously, you need Prim's algorithm to solve this problem efficiently. So I'm just going to give some of the background in case you don't know it. So basically, let's say you have a graph, and in this case, we have a graph with 5 nodes or vertices, right? And to connect all of these nodes together without forming a cycle, so we want every node to be connected together, but we don't want to form a cycle. How many edges is it going to take us to accomplish that? It's going to take exactly n minus 1 edges. So if we have 5 nodes, it's going to take exactly 4 edges to connect all of them together without creating a cycle. Because take a look right now, I have 4 edges, right? If I add another edge that's not a duplicate, if I add an edge here, we create a cycle. If I add an edge here, we create a cycle. If I add an edge here, we create a cycle, right? That's just kind of something and I think it intuitively does make sense because, if you start out with 5 nodes, you add 1 edge, now we have 4 different, connected components. We have one here, one here and then a couple here. Every time you add an edge, you're decreasing the total number of connected components by 1. So if we start out with 5 nodes, we add 4 edges, we decrease the number of connected components by 4, then we're going to be left with 1 connected component. So if we add another edge on top of that, we're going to get a cycle. So we want to connect all of these without creating a cycle, because that's what a minimum spanning tree is. So our goal is to connect all of these with exactly 4 edges, but Prim's algorithm, or the definition of a minimum spanning tree, is also one more condition. We want to minimize the total cost of the edges. Now, I didn't actually draw all of the edges, all of the possible edges out right now. It would look something like this, right? Basically, for every single node, it could possibly be connected to every other single node. And the reason I'm not drawing it is, as you can see, it's going to get really complicated really quickly. So this is pretty much what it would look like if I drew every possible edge that could exist in this graph. And I think that's going to make it a little bit too messy, but let's just assume that those edges do exist, that for any point we could possibly connect it to another point. So the way Prim's algorithm works is we can choose to start at any single node in the entire graph, and then very simple, we're just going to perform a BFS, a breadth first search, on that node, where we are going to continuously for every node that we're adding, we're going to have 2 data structures. We're going to have a visit data structure to make sure that we don't add the same node twice, because if we add the same node twice, that's how you know we're going to get a cycle. We want to avoid cycles. The second data structure we're going to use is a minimum heap, which is going to keep track of our frontier of our breadth first search. Now, what is a frontier? Well, you might know that, let's say we had a single node. So we visited this. This is in our graph, right? This is part of our minimum spanning tree. What's the frontier then? Basically, every possible node that could be added from this position, right? So initially, if we just had one node, these 4 nodes would be in our frontier, but we're not just going to have each node in the frontier. So we're going to have, let's say node 1, and we're also going to add the weight of connecting node 1. So let's say the weight of the edge was something like 5, then we'd add 1, 5 in our min heap. But we're not going to add it in this order. We're going to add it in the opposite order, 5, 1, because when we're popping from the min heap, we're going to be wanting to pop whatever node we can connect next with the minimum possible cost. So let's say we had 5, 3, 2, and up here we have a 6 or something. Out of all these 4 nodes, which of them can we connect with the minimum possible cost? That's what we're going to use our min heap for. Looking at it, you can tell, okay, this one, because it has a cost of 2, so then we're going to connect that. So then that's going to be a part of our frontier. So next, we're going to say, okay, we have 2 nodes, a part of our frontier. Next, what we're going to do is add more nodes to our frontier. Even though we already had all 3 of these nodes, we're going to add them again to our frontier, because now possibly if we're starting from node 4 and we're trying to connect to 3, 1, or 2, it's possible that the connection from 4 to 3 or 4 to 2 or 4 to 1 could be smaller than the connection from 1 to those respective nodes. So we always want to connect a node with the minimum possible cost that it takes us. If it costs less to connect it to 4 than to connect it to 1, we're going to take the one with the smaller cost. And of course, as we visit nodes, we visit 0, we visit 4, we're going to add them to our hash set so that we don't, starting from 4, we're not going to go back to 1 and add 1 again, because that would create a loop. And how do you know that we can stop the execution of Prim's algorithm? Well, once the length of our visit set, the number of nodes that we've added, is equal to 5, which is the number of nodes that we started out with. So with all that being said, you just have to understand how these data structures are contributing to the solution, and then we can go ahead and walk through it. So let's start at 0. You can start at any node. You can start at 3, 2, 4, but in this case, we're going to start at 0 just because it makes sense. So when we start at 0, what we're doing is we're adding it to visit, and we're adding it to the frontier. So what's the cost of connecting 0? Well, if we're just connecting a single node to the graph, we're not actually including any edges, so the cost is going to be 0, and the node value is going to be 0. And so the way this algorithm works is at each step, we're just gonna pop from the min heap. So let's pop the first value, this, right? So the total cost so far is 0, right? We don't actually have to add any cost. And that's actually one other variable we're gonna be maintaining. Let me just write it down here. So far the cost is 0. We're gonna continuously be adding to it though. But next, for 0, we're now gonna add every one of its neighbors to the frontier. And the way we're gonna add it, I haven't drawn it out, but there is gonna be like an adjacency list. So we will have a list of neighbors for 0. Of course, it could be connected to every single point in the entire graph. That's just how this problem is defined. Now, I'm not going to write the exact cost of each of these edges because I think it's pretty obvious from the picture that this is going to be the one that's closest, and the cost of connecting to that is going to be 4 based on the point values that we were given in the previous picture. So out of all these 4, these are going to be in our frontier. So all of these are going to be in our frontier, and you can see I drew them here. I didn't specify the actual cost of 2, 3, and 4. Because I don't want to focus too much on that because we know that this is going to be the minimum. So this is the one that we care about right now because we already can tell from the picture that it's the smallest. And so that's the step, right? So you take the entire frontier, add it to the min heap. Next step, we're just going to repeat the same thing that we just did. We're going to take a look at our frontier, pop the minimum from it. We know that this is the minimum, so pop it. When you pop a node, we have to add it to visited. So we popped the 1 node, right? And so we're going to add it to visit, and the cost of that one was 4, right? So let's just add 4 to our total cost so far. And since this one was popped, let me just draw that is definitely going to be an edge inside of our minimum spanning tree. So now we are at 1, and now we're going to add every adjacent node or every neighbor of this to our frontier as well. So you can see that this is kind of what the graph is going to look like. We're not going to add 1 to our frontier because it's actually already been visited, but we are going to add 2, 3, and 4 to our frontier. Now notice they already exist in our frontier, right? So we're going to be adding them multiple times. That's kind of how the n squared is going to come from, right? We could possibly add n squared nodes to this min heap because we're going to be adding it for every possible edge that exists in our graph. And every time we pop from the min heap, it's going to be log n. So basically the time complexity is n squared multiplied by log n. So I'm not going to redraw all 3 of these nodes, but you can assume that yes, there could be duplicates of them inside of our min heap. Now looking at 1, which node is the closest to it now? Of course, 3 is the closest node to our entire graph. This is our entire graph, right? We have 2 nodes, right? What's the closest node that we can add to this graph, right? We could add it anywhere. We could say, okay, this is going to be connected to 0, right? Or 3 is going to be connected to 0, or 3 is going to be connected to 1. We could add any node, but we know just by looking at the picture that this is what's the closest is going to be. And I'll just tell you, okay, for that node 3, the cost is going to be 3. So now we continue another iteration of our loop. Let's pop the minimum from the frontier. This is going to be the minimum. 3 has been popped. So let's add an edge connecting it to our graph. So far, this is what our graph looks like. Since we popped 3, add it to visit, and let's add the cost of it. So 3 was the cost of adding node 3. So total, our cost is going to be 7 so far. So now 3 has been visited. Now let's add the frontier of the neighbors of 3. Of course, 1 and 0 have already been visited, so we're just focusing on 2 and 4. We're going to add those to our frontier. They're already in our frontier, but yes, we're going to be ending up adding duplicates to the frontier, right? So I'm not going to, actually focus too much on the drawing, but there could be multiples of these in the frontier. And now, well, which of these edges that are in our frontier or the nodes in our frontier, what's the minimum cost that we could pop? I'm just going to tell you that for the cost of node 4, it's going to be 4, and it's going to be this, right? You can tell by the picture, that's pretty obvious. This is going to be the shortest way to include the node 4. So let's pop this node, add it to the edges list. So 1 or 3 and 4 are going to be connected. And the cost of that one was 4. So let's add 4. And let's add it to the visit. Now, just so you know that let's say we did end up popping the same node multiple times, because technically that's possible, right? We pop 1, 4, but we still have a 4 remaining in the frontier. So what if we popped 4 again? What would we do? Well, we would actually see that, okay, let's take a look at our visit. Well, 4 has already been visited, right? So there's no need to add this to visit again, and there's no need to add the frontier of that again, and there's no need to take the cost of that and add it to our total cost because 4 was already connected to the graph. We don't want to, add a redundant cost. Okay, but so now you can see that 4 has been added to our graph. Now, what's the remaining neighbors of 4? Of course, these 3 nodes have already been visited, so the only edge we could possibly add that would be useful would be this to there. But you can see that that's a pretty long path, right? Surely we have a shorter path in our graph to the 2 node. So you can see 4 of them are already connected. We just need to connect one last one. So let's pop from our frontier again. This is going to be, obviously 2 is going to be the one that's popped, but what exactly is going to be the cost of it? Well, I'll just tell you the cost is going to be 9. And which edge is it going to be? Well, by looking at the picture, we'd probably think one of these 2 is going to be connected to 2, either like this or like this. And I'll tell you that the paths are actually not of equal length. If they were equal length, it wouldn't really matter which one we chose, right? It would lead to the same cost anyway. But in this case, I'll tell you this is the shorter one. So, and yes, the cost of that is going to be 9. So we can pop this. So we can say, okay, 2 has now been added. 2 has been visited. Now it wasn't previously visited, but now it's visited, and the cost of adding it was 9. So the total cost that we ended up getting was 20. 20 was the total cost, and now we know we're done because every node in our graph has been connected. You can tell by the red edges, all of the nodes are connected. We added 4 edges, and we visited every single of the 5 nodes. So the algorithm, Prim's algorithm, is just that simple. I mean, it's not really simple until you've actually done it a few times. You've practiced it and learned these concepts of visit, min heap, and now we're actually going to jump into the code. It's about 20 to 30 lines. Okay, so let's write it out. And like I said, so the first thing we're going to be doing is actually creating the adjacency list because that's not given to us. We're just given a list of points. So I'm going to get the number of points we have, and then I'm going to start creating that adjacency list. And basically I'm going to refer to each point in our list as basically the index of that point. So the first point in our points list is going to be point 0. The next one is going to be point 1, etc., etc. So we can just say for I in range of the number of points we have. So for I in range of n, the number of points, we're basically going to take each point I, map it to a empty list so far. Now we're actually going to build out that list. So for I in range of n, so for every single point, we want to compare it to every other point in the graph. So for j in range I plus 1 all the way to n. So we don't want to compare each point to itself. We just want to compare it to every other point in the entire graph. And when we do that, we want to get the coordinates. So for the point at I, we're just going to get the x and y coordinates. So points at index I. And we're going to do the exact same thing for the point at index j inside of our loop. We're going to get each point that we're comparing it to. And then we're just going to take the distance, the Manhattan distance between them, and we can get that by taking the absolute value of x1 minus x2, the absolute value of y1 minus y2. And so I'm going to just comment up above that for each node, we're mapping it to a list of points. And for each point, we're basically going to have the cost and the node or the neighbor. Each neighbor is going to be a pair, right? So each edge is basically a weighted edge. Don't forget about that. So we're going to say adjacency for I, append to it the cost or the distance, right? And the node itself, which is node j. And we're going to do the exact opposite because technically these are undirected edges. They go both ways. So let's just do the exact opposite. So adjacency of j, append to it the distance, same distance, but instead we're appending I because that's its neighbor. So this is how you build that adjacency list. And technically we could actually not have to write this for loop out. We could actually compute these calculations while we are running Prim's algorithm. But the reason I'm doing it before is just to give a clear distinction. This is the edge portion. This is like the extra portion of this problem. The following part is literally just an exact implementation of Prim's algorithm, nothing fancy. So let's define our variables. We're going to have a result, which is of course going to be the total cost. Initially, it's going to be 0. We're also going to have a visit set. So it's going to tell us the points that have already been visited. We're also going to have a min heap, which is initially not going to be empty. We're going to be starting at point 0. And the cost of it is also going to be 0. So let me just put in a comment that each pair is going to be the cost and the point. Cost goes first. The order is important because that's what the min heap is going to be minimizing it based on. And so now we're actually going to do the loop. And remember, we're going to keep going while the length of visit is less than the total number of points, which is n. And on each iteration, we're going to be popping from the min heap. In Python, we can say heap q.heap pop. And from it, we'll get a pair of values. Okay, we have to specify which heap we're popping from, min heap, min h. And we're going to get a pair of values. We can call it cost, and the point, let's call it I. And remember, we are adding duplicates to our min heap. So if we popped it, this could have already been visited. So let's just check if I is in visit, then we're just going to skip this iteration of the loop. We don't want to have to process this same node that's already been popped before. But if it hasn't been popped, then we're going to take the cost of it, add it to the result. So we're adding this fresh new node that we haven't visited yet. And we're also going to add it to visit now to make sure that it never gets visited again. And then we're going to go through every neighbor in its adjacency list. So the adjacency list of I. And remember, each neighbor actually isn't just one value. It's going to be the cost. So let's call it neighbor cost, as well as the neighbor. Right up above, you remember that in our adjacency list, we added a pair of values in that list, cost and the node itself. So now for each neighbor, so for nay, if the neighbor is not in visit, then we're going to be adding it to our min heap. So then we can say heap q.heap push to the min heap. We're going to be pushing a pair of values. Remember, we're pushing the cost first, so neighbor cost, and then the neighbor. And that's it, right? So we're just, for every neighbor, all we're having to do is just add it to the min heap, right? And then we're going to go to the next iteration of the loop, repeat the exact same thing until we visit every single node. Once we've done that, we know for sure the result has the total cost that it took. So then at the end, all we have to do is return that cost. Let me make sure I don't have a space. And yeah, that's the exact thing. So you can see this is the portion that's Prim's algorithm. Everything else is just some pre-work that we had to do. Yes, we could have taken this pre-work and mixed it up into here, but I just wanted to give a clear understanding to you all of what exactly Prim's algorithm entails. This is just stuff that's not necessarily related to Prim's algorithm. We do need an adjacency list though to perform this algorithm efficiently. So I hope that this was helpful. If it was, please like and subscribe. It supports the channel a lot, and I'll hopefully see you pretty soon. Thanks for watching.